Hi, I'm Dr. M. Kamaksha, open source software evangelist and also a full stack web developer. I am also an academic of data science and analytics. For the past few sessions, I have been talking about using R programming language for data analytics, and I taught about data types and descriptive analytics and also a few bivariate statistical techniques like two sample t-test, crosstabs, and also correlation, like both bivariate and multivariate correlation. And in this video I decided to talk about simple linear regression. Now, what is this simple linear regression? You have straight away go to the Wikipedia, as usual, I pick most of my data from Wikipedia. You can you can pick up the definitions, characteristics, and different types and methodology behind this simple linear regression. By the way, if you have, let me put it in short, if you have one single variable, left hand side and right hand side of the equation, then it is simple linear regression. And if you have multiple variables, number of variables in RHS, it is called multiple regression. You have different ways to perform the regression analysis, like logistic regression, ordinal regression, and probit regression, and there are GLM, generalized linear modeling. There are many things. They are unending. Today regression is highly developed areas of topics in statistics. But whatever the technique, it just boils down to a particular procedure where we try to calculate two measures. They are constant and coefficient. You see here you have an objective function. This is the objective function. In this equation, this is actually a regression equation in which this is not the thing I have somewhere here. I came far down. So this is actually the regression equation of the population. In population we mention the y is equal to alpha plus beta x, where y is a dependent variable. You also call it as regressor, and then alpha is a constant, beta is a coefficient. In other words, we call it as slope. There is a variable called x, which is a predictor. So y is a dependent variable and it depends on x, which is an independent variable. Other names for this y and x. Y is also known as regressor and x is known as predictor. There is also explanatory variable and exploratory variables. There are different names for these variables, but this is just a simple equation, linear equation in mathematics. It is in the form of y is equal to mx plus c, something like that. This c is, so whatever it is, in this equation you have two parts, LHS and RHS. In LHS you have dependent variable, in RHS you have a constant and an independent variable and then an error. There is an error term. This is a full-fledged equation. Y is equal to alpha plus beta x plus e. E is an error. Now all the effort in regression is just to estimate these two values, that is alpha and beta. Alpha is a constant and beta is the slope. Okay, that is what is the duty. And then we try to perform some tests so as to determine that whether this alpha beta are statistically significant or not. This is what I'm just going to, honestly speaking, this is what I'm just going to cover in this session. There is unending explanation. We can keep talking for days and days about this regression, but it is not possible for me to keep my demos flowing on and on for a few days. I just wanted to explain the entire gist of simple linear regression within a single demonstration. So as I said, this is what these two values is the object of determining these two alpha comma beta is the object of the goal of regression analysis. that too in simple linear regression analysis. Let us jump into the action. Now, I'm sorry, I don't know why I opened this. Let me explain my demo data sets. Did I open this? Let me close. Now I have a data set. Actually, where correlation ends, there regression starts. That is the fundamental belief in statistics. Okay, where are my, here I have data sets. Now I have a data set called inflation. Let me open this and show you. So I was performing correlation, and this regression is just the continuation to my previous topic, correlation. In my demos related to correlation, I explained as how to find the associations between two data sets, namely HDFS, HDFC and Access. Now these data sets, I have the data for few months. Now in this data set I have 3 columns. Of course it is not a big data set, just a few rows of data. We have only 5 rows of data, which is not sufficient, but unfortunately I could not get sufficient data for this example. If you have sufficient data, then you try to experiment simple linear regression on your I'm going to explain both simple linear regression and multiple regression, and the assumption for the model in this data is going to be like this. The stock prices of X, it is not possible for me to explain multiple regression. I can explain you the simple linear regression using this data set. The assumption goes like this: the stock prices depends on inflation, as usually. Like, I don't want to delve into the theory as how they depend and to what extent. In finance, we can make an assumption that the stock performance of a company or a firm might depend on inflation. It depends on several factors, but one of the potential factors are inflation. Now we are going to test this assumption that the stock performance of a bank depends on inflation, something like that. You see the values, or actually the inflation is shown in percentages. I return the percentages into the actual values by multiplying them with 100. Okay, so that I can normalize and bring both of them close together. Now let us open this data set into R. Let me go back to my R. Now here, so reg data, and now read CSV file choose. Now enter. Let's go to the folder where we have this regression data sets. Think this is an inflation data. Inflation. Now let's see. Now we have the data inside here. Like that. Let's see. Control L. I think I don't need all this. Yeah. Now reg that. You see, we got the data. We don't need this calendar year, the date. We just want these 3 variables. Now how to perform the regression? Now if you want to perform the regression, in R you have a base function called LM. This is linear model or modeling, whatever it is, I don't know. Help LM. Now you will come to know the documentation for this function. This is fitting linear models. Maybe LM stands for linear model, something like linear models. LM is used to fit linear models, something like that. Now you have the formula. We need to supply a few arguments to this function. One of the arguments are formula. Then we need to minimum, at least we need to give these 2 arguments. One is the formula, the other one is the data, and there are quite a few other things which we can mention, but for time being I am not interested in all these things. This is just sufficient. Now you have quite a few examples, not many, but very few examples here. You can just go into. I think I already explained what is the formula in while I was explaining ANOVA. analysis of variance in one of my demonstrations. The formula refers to R formula, something like this. Formula is going to have, it is just a every mathematical formula has a R syntax, and we'll be using R syntax to define the formula. Now y is equal to alpha plus beta x, that is the formula for regression. Now that formula we need to convert it to the R formula so that R can understand. Now I'm going to perform simple linear regression between HDFC stock prices and inflation for I think 5 different months. We just have 5 months data. That is not sufficient, but this is just a demonstration. I just don't like to bother much in getting the data. Maybe you can do a simple linear regression on your own data sets. Now the assumption is going to be HDFC stock performance depends on inflation. Inflation does not depend on HDFC. That is not correct. Now what is going to be the hypothesis? Okay, let me talk about the hypothesis after performing the simple linear regression. As I said, I call it as fit. I already have, okay, it's not because I use this word fit when I was performing AOV, but doesn't matter. Anyway, I finished with those sessions. I can reuse this name fit LM. Now HDFC depends on inflation. Oh my god, inflation. I don't know, that's obnoxious. Now data is equal to reg dat. Now let me press enter. That's all. This is just simple linear regression. This is the formula. This is LHS the formula. In LHS you have dependent variable. RHS you can do hell lot of analysis. Believe me, you can do hell lot of analysis. I'm just trying to put it as simple as possible because I can't explain each and everything related to simple linear regression. This is the simplest way we can perform simple linear regression with the help of this statement. So this is the statement which we, let me press enter. Now R is silent, which means it does something. You see, let me see what is there in this object fit. Oh, that is fantastic. We got the intercept. This is the intercept, which is alpha. This is the beta, which is the slope. Oh my god, there is the slope is negative. Shall we plot the data and see scatter smooth? Okay, plot reg dat. It's going to be 3 HDFC, and then in reg dat 4. Now let's see. Yeah, this is only 5. Its type is L, line chart. Oh my god. Let me go for scatter smooth. I can think it's not plot. Scatter smooth. It is a trend. It shows. Oh, smooth scatter. Okay, type. I think we don't have type here. Smooth scatter? No, it's not smooth scatter, I guess. This is scatter smooth. I don't know, scatter smooth is not working, but so we only have to, one is why scatter smooth is not working. WN is a function called, okay, because we have 2 less data for, so it's not working. So only thing is plot. Yeah, but the plot is not useful for us. Anyway, I think this is downwards. You see here, you got okay. Well, anyway, we make these plots later. We don't need to. I don't want to need to. So you have fit, and in this fit you got intercept and inflation. I mean the slope. But let us use summary, just like we did in analysis of variance. You got entire information now. You see, this is the formula. I mean the statement for simple linear regression. You have residuals, that is not important for us. You have coefficients. Now this is you see the intercept, and this is slope, this is negative, which means it is downward curve. You have standard error, t-value and p-value. Now why do we need all this information? Anyway, alpha, beta, okay, we calculated these two values, but we just came to understand that we have very huge size. Alpha is highly robust, and it's not robust actually, an obnoxious value. We can't afford to have this kind of value. Now slope is very important because this talks about the direction. It is negative because, and which means that it is downward. Every value in HDFC reduces, go down for every increase. Every increase in every increase in inflation gets HDFC value down, decreases HDFC value, something like that, inverse relationship. Now this is the standard error. The estimate divided by the standard error yields t-value, and this is the p-value for this t-value. Now what do we need to do with this t-value and p-value? That is what is the focus of the discussion. Whenever we perform the regression, we need to test a hypothesis that the alpha is 0. That is null hypothesis. The null hypothesis, though you have some certain effect in sample, but the actual null hypothesis could be alpha is 0, and for beta, null hypothesis is going to be beta is 0. So these are the null hypothesis, and obviously the alternate hypothesis is going to be alpha is not equal to 0, beta is not equal to 0. So why do we need to do this statistical test? Because we are in suspicion that though we have some certain value in sample, but in truly this is not a true value. In population this can be something different. Now coming to as usually, as I always straight away go to the p-value and pick it up and compare with the threshold value. Now when you compare this value 0.02, which is less than 0.05, which means at 5% significance level this value is statistically significant, which means we can reject the null hypothesis that the alpha is 0. No, it is not 0. The value which we calculated from the sample appears to be a true value. It's not a fictitious value. We don't have the sampling error. Now when you come to beta, that is not the case. You see the p-value is more than 0.05, which means at 5% significance level we fail to reject the null hypothesis that the beta is equal to 0. And it is true. You see here we got the negative value, and your p-value is saying that it is close to 0, which means it's less than 0. So we fail to reject the null hypothesis that beta is equal to 0. In population, though you got some negative effect in your sample, but in population the true value can be 0, something like that. Okay, this is how we perform the statistical test, the hypothesis test in simple linear regression. Now suppose if you have some categorical data, fortunately we don't have that, you can also perform AOV fit, then it will return you back the summary. AOV fit will but anyway, let me not talk about this. I don't have the categorical data. I am not talking about analysis of ANOVA. You can also extrapolate extend your regression analysis and create an ANOVA table in case if you have categorical data. So we don't have, that is not the case in our data. Both of the variables are. Now there is an interesting aspect of simple linear regression, that is plots. Suppose if you use the method plot on fit, then your R will ask you, do you like to, there will be 4 very excellent plots. You see this is the first plot called residual versus fitted values, and the second plot is going to be the normality tested. These are the assumptions. Actually the first assumption is going to be the residual versus fitted. This is there must be equal number of data points above and below this 0 line, and then there is a normality. This plot will show you whether your data satisfies the normality assumption or not. Here you see there are 3 culprits in your data, that is 5, 4 and 3. Now let us again press last time, and this is the scale location, and this is the final plot, the fourth plot, residual versus leverage. This is called leverage plot. Okay, it takes quite a lot of time. I need a little bit more time to explain each and every graph of this. Okay, but I don't think I have sufficient. Okay, let me take you online and show you how to interpret regression plots in R. Okay, these 4 plots deals with 4 different assumptions, and understanding the diagram, you can go to any source, it doesn't matter. Any some valid, you can see the first one is the residual versus fitted. You see here, this is the first one. This plot shows if residuals have non-linear patterns. One important and fundamental assumption, actually we need to test all these assumptions well before performing the single linear regression. The residuals always must be non-linear. In simple linear regression it should be linear. If it is non-linear, then simple linear regression is not suitable technique for that situation. That particular assumption can be observed with the help of residual versus fitted graph. Let's go back to our graph. In here we have residual versus fitted. I don't think we are the relationship seems to be linear because we have equal number of points on and above and below this horizontal line. And let's go to the second plot. This is as I said, normality assumption. The relationship between, we are using 2 variables in this simple linear regression, and the relationship between these 2 variables should be bivariate normal, and both of them should obey with the property of normality, and both of these variables should satisfy the bivariate normality. Now you see here these data points are not exactly on the diagonal line, which means that they are roughly just above and below. They are roughly normal or not normal. So at best I can say not normal, or we can also assume that they are roughly normal, something like that. And the third one is the scale location. You see here this plot. Okay, let me take you back to scale location. Spread location plot, and this plot shows if residuals are spread equally along the ranges of the predictors. This is something like there is a particular assumption. This particular plot speaks about the homoscedasticity. This is not quite meaningful for the data sets in which we have interval and ratio data. Suppose if you have some group data like categorical data, there is a particular aspect called homoscedasticity, which means the variance across the groups are different. So we'll be testing that assumption with the help of, this is a visualization. A visual scale location plot is a visual inquiry to verify this assumption known as homoscedasticity, which means usually from this plot these values must be spread across the plot. There must not be a particular pattern. You see here you got a downward declining pattern. The curve is declining downward. That is not a good observation. So this should be a horizontal line. Then it satisfies the homoscedasticity is not present in our data. Otherwise, so now here if you look at this data is sensitive. It is not satisfying the third assumption that the data is free from the homoscedasticity, which means there is a problem of variance in this data. That is what in equal variance all the groups I mean the variance of the LHS variable should be equal to the variance of the RHS variable, and but that is not the case in this regression fit. Okay, the last one is the residual versus leverage. Here we'll try to find out the culprits. From here we can do a hell lot of research on this simple linear regression fit, but I just explain this fit and stop my demo. This particular plot talks about the outliers. This plot is very much useful for us to, I don't have the time to read each and every sentence from here. You can just go to any particular valid portal and start reading for each and every plot. I just briefly talk about here. If you see, like, there are few data points, 3, 4 and 5. These 3 months, we have 5-month data. These 3 months are outliers in our data. You see here, let us go back to the data, reg date. You see the month 3, 4 and 5. The error in our simple linear regression is very much due to these 3 months. So these data sets, these data variables, these data rows. So what we need to do, let me go back. I think I didn't use, I used a summary. You see here in summary you have multiple R squared value and adjusted R squared value. Both of them should be very close, but that is not the case in our example. Now you see the R squared value is only 0.49. That is not a good value. It should be close to 1. 0.49. That depends on the situation. In some situations that may be a big value, but in some situations it's not a big value. But I'm sure that this R square value of this size is never a good value. In simple linear regression it should be close to 0.9, and adjusted R square value is also not close to the multiple R square value, which means that we have considerable amount of noise in our data. Now suppose if you remove these 3 data points, I mean we have very short data, and I'm talking about removal of the rows. That is not going to do much good to it is totally a senseless thing. But usually whenever you find outliers like this in your analysis, what we do is we come back to dataset and we delete these variables. I'm sorry, I'm calling variable, I don't know, in this row, and then again we go back and fit the data. We perform the simple linear regression and we go back and check the R square value. If the R square value increases, then we consider that these outliers are truly outliers and they need to be deleted from the dataset. That is one utility of this visual residual versus leverage. Okay, so I'll stop my explanation here. We can talk for days and days about regression, because regression is very highly influential statistical techniques in analysis, data analytics. I think this is the right time to stop my demonstration. I explained about how to perform simple linear regression on a dataset in which we have very few data records, only 5 months based data, and I explained how to interpret the regression outputs using 2 different the statements. Okay, that is for this video demonstration. Thanks for watching this video. Stay tuned to the new content. Keep watching for the new content. Please press like button and subscribe to my video channel.